Hello everyone, welcome to Calculus 1, and in this part hopefully we will get a calculus started. Again, before calculus, we have a little more material to review, and still I want to mention slope. Slope, it is very important, okay, in calculus. And also I said you can consider in a simple way after the first day of class. If people ask what you have learned in calculus so far, you may want to tell people you know derivative, and the derivative is slope. There's nothing wrong with that statement. Indeed, it is a very good statement for beginners, really. Derivative with its slope. In calculus, we study three things: limits, derivatives, and integrals. Derivative is slope, okay? So slope really comes from the idea of a line. And also, let's talk a little bit more about the quadratic functions. Quadratic function, it is generated by two power functions, x squared and x. Okay, the graph of quadratic function, it is a parabola. Remember, the parabola could be the case opening upward or opening downward. Sorry, I cannot make that thing to happen for now. I hope you understand the idea. And the way is, how do we know when the parabola opens upward or downward? It's very easy. You look at the leading coefficient. If A is positive, that means the parabola opens upward. And if A is negative, then it's going downward. The parabola opens downward. And another very big issue is, how do we know the vertex of the parabola? And I suppose you remember, any quadratic function, this is maybe the standard form of quadratic function, always can be converted into vertex formula. And I'm going to leave that for you to figure out how you convert a quadratic function to a vertex formula. Okay, this is also very important because I'm doing this part just for reviewing purpose, so I'm going to leave that to you. Maybe you can think about one or two examples or pick up some exercise problems from the textbook to see if you can complete a task, convert a quadratic function into a vertex formula, and then draw the graph. Okay. So for this part, I hope you understand. I'm reviewing the types of functions. And so far, believe it or not, I only did one type, power functions. Indeed, power functions, they do form a bigger family of functions. And indeed, in many ways, they are just totally different functions. All these are power functions, and indeed, we have many more. And also, I said, like the linear functions, quadratic functions, or in general, the polynomials, they are generated from power functions using addition, subtraction, and multiplication. And if also we consider the division, then we have the rational function. A rational function, it is a quotient of two polynomials. Okay, the first big family of functions, that's the power functions. And they do cover a lot of functions. Many times, believe it or not, you may have a function look very weird, but still, it is from power function. And also, we do have a lot of functions not from power functions. So we do have the exponential functions, b to the x, and this is an exponential function. B is considered as a constant, x is a variable. Like for example, 2 to the x is an exponential function. 2 to the power of x, it is an exponential function. Then think about the other case, quadratic function, x squared. 2 to the power of x squared, they are different, right? 2 to the power of x, it is an exponential function. X squared, it is a power function. Okay, I make sure you see the difference. And also, many times when we consider exponential function, indeed we consider the exponential function e to the x. E, it is the Euler's number. E, it is the Euler's number. Okay. And also, we have the inverse function of exponential function, the logarithm. And the log base b of x, it is a logarithmic function. And many times when we consider a logarithmic function, it is the natural logarithmic function, ln of x. ln means log base e. It's right here. Exponential functions, logarithmic functions, they are mutual inverse functions. So I think that's all for reviewing purpose. Some multiplication formulas and factorization formulas, exponentials and logarithms, and types of functions. Types of functions, it's pretty important because later on we are going to have derivative rules, we're going to have integral rules. Basically, those rules, they are just the rules for some specific types of functions. Okay, let's get a calculus started. I think, well, hopefully you still remember what I said earlier. Derivative is slope. So for this part of material, mostly I just pick up the content from section 2.1. It's a very quick preview of calculus. Okay, preview of calculus. And in calculus, put in a simple way, we are going to learn three things in calculus: limits, derivatives, and integrals. Okay, then what is a limit? What is an derivative? What is the integral? And so this is where we are going to start. We are going to start in a very simple case. Lines. Each line has a slope, right? Overall, in general, when the line is going downward, moving from left to right, we understand it has a negative slope. Indeed, if we read from the function, we know the slope it is negative too. As you expected, it's a negative slope. The second chart right here, we are having line going upward. But anyway, I guess it's not going up too fast. So and then if you read the function right here, we know the slope it is 1/2. And the third chart here, it is special case. It is horizontal line. Remember, slope, it is defined as the ratio of rise and run, rise over run. And indeed, it's horizontal line, no rise at all. So indeed, in this case, the slope, it is 0. Slope, it is 0. And also, if you look at the equation, even though it says constant, you can consider that it is 0 times x plus 2, right? So slope is 0. It's easier to understand the slope of line. And then the issue is, what would happen to a curve? So this is the graph of the parabola, y equals x squared. And also look at the trend or the pattern of the curve. I'm saying look at look at this part, the left part of the curve, to the left on the side of the y-axis. Overall, we can say the slope, it is negative, right? The curve is going downward. And also, if you can track closely out the side, you move somewhere up there, you can see the trend of the pattern I'm seeing, it's going downward somewhat at a fast rate. And moving down over here, maybe still it is going downward, but anyway, roughly I can tell it is going down at a slower rate. Okay, and then it moves around to the right side of the y-axis. I'm saying the overall the pattern now it is going up, right? And this, even though it is going up for this entire right half, but anyway, still there's the issue. I figure out, I see maybe to this point, it goes up at a slow rate and moves up again, it's going up at a faster rate. So the issue is how do we find out the slope of a curve? Well, to answer this question, you will have to look at the curve carefully. And also mathematically, to answer this question, we're going to say whenever we have curve, at least for now, let's say we are having a smooth curve, not those zigzag type of things, okay? A smooth curve like a parabola. And then one interesting here is for a smooth curve, you always can, at any single point on the curve, you can draw a line which touches the curve exactly at one point. And that line to the curve, It is called as a tangent line. Or simply put, a tangent line, it is a line touch the curve exactly at one point. And at a different point, there is a different tangent line. And also the slope of the tangent line. The slope of the tangent line, it is considered as the slope of the curve. The slope of the tangent, it is considered as the slope of the curve. Okay, and now let's take a quick look how we can consider the slope of a curve. Slope of curve, which really means we need to consider the slope of tangent, right? Then keep in mind that the issue here is the tangent only touches the graph exactly at one point. Let's say we can choose at a particular point. Let's say it is at any curve at a point of an ordered pair. Let's say we do know the function a and f of a. And then this is the line you are seeing here. It's not a tangent. I'm trying to say it should be a curve. Yeah, I think somewhat I might miss something there. Well, maybe. Yeah, maybe this will help to better understand the situation. The tangent touches exactly at one point. And in this part of the curve, you can see it's touching the curve at 2 points, intersect the curve at 2 points. So this is secant line. And indeed, this is also secant line, okay, if you check closely. But anyway, let's say this is just one to show the idea. We say this is tangent line. We can say it touched the curve exactly at one point. And then the slope of the tangent, because we only have one point, it will be very hard to figure out the slope of the actual tangent. So what we can do here is we can choose a point which is not too far away from the given point on the curve. The orange line here. So accordingly, you can tell the orange line at least it intersects the curve at 2 points, at least 2, even though you can check here there's another point over here, okay, in this case. But anyway, 2 points, at least 2 points. So the orange line, it is considered as the secant, okay. And then, I suppose, because when we have 2 points, we can calculate the slope. Slope, it is considered as rise over run. So we always can calculate the slope of the secant. And the thing here is, well, clearly, I would say if you look at the orange line, I'm not convinced it's anywhere close to the tangent. But anyway, we can choose the other point somewhat closer to that given point. So the green colored ordered pair, roughly green, okay, I know it's not totally green, roughly green colored ordered pair here. Okay, when you choose this closer point, then you have another secant line. I am seeing this secant line should be closer to the tangent. So indeed, as I'm saying, in general, the slope of the tangent could be approximated by that of a secant. And indeed, the approximation can be improved by choosing a point closer. Choosing a point closer to that given point. This is the way how we consider the slope of a curve. Let's take a break. Thank you for watching.